The speed of light is the rate at which light travels through empty space. It is a fixed number, not a rough description of very fast. That number is 299,792,458 meters per second. Scientists did not invent this number. They measured it because for centuries nobody actually knew whether light arrived instantly or took time to travel. That question mattered for astronomy, for timing systems, and eventually for almost every piece of electronics you use today. Once the speed of light was pinned down as a fixed, measurable value, it solved a real problem. It explained why signals, satellites, and even your own eyes are always working with information that is slightly old by the time it reaches you. Everything you see and everything you receive over a distance already happened a little bit in the past. This idea sits underneath a long list of everyday technology, and once you understand it clearly, a lot of things that used to feel confusing start making sense. Fiber internet, satellite phones, GPS navigation, camera lenses, and even the images astronomers publish from deep space all trace back to this single fixed number. None of those systems are working around the speed of light. They are all built directly on top of it, using it as a known, dependable constant rather than a variable that shifts from one situation to the next. Here's what's actually happening once you break this topic down into its individual pieces. Light is not instantaneous. It takes measurable time to travel any distance, even short ones. This matters because people assume light just appears everywhere at once, the way a light switch feels instant when you flip it in a room. It is not instant. It only feels that way because the distances in a room are tiny compared to how fast light moves. Consider a fiber optic internet connection running between two countries. Even with a perfect connection and perfect equipment, there is a minimum amount of time the signal needs just to physically cross that distance, and no amount of better hardware removes that flaw. If you run a business that depends on split-second international transactions, that delay is not a bug you can engineer away. It is physics. Light travels fast, but not instantly, and that gap shows up the moment distance gets large enough. The exact value of the speed of light in a vacuum is 299,792,458 meters per second. This number is fixed and defined, not an estimate that gets refined every few years. This matters because it is used as a reference point throughout physics and engineering, including in how we define the meter itself. Think about a laser rangefinder used on a construction site. It works by sending out a pulse of light, timing how long it takes to bounce back, and using the fixed speed of light to calculate distance. If that constant were even slightly wrong, every measurement taken with that tool would be off, and a contractor could end up ordering the wrong amount of material for a job. The speed of light is not approximate. It is one exact number that engineering tools depend on to be accurate. This speed stays the same for every observer, no matter how fast the light source or the observer is moving. This matters because it goes against normal intuition about how speed works. If you throw a ball forward from a moving car, the ball's speed adds to the car's speed. Light does not behave that way. Whether the source is standing still or moving towards you at high speed, you always measure light arriving at the same fixed rate. Think about a satellite orbiting the Earth at high speed while sending a signal down to a receiver on the ground. Engineers do not need to adjust their calculations for the satellite's motion, changing the speed of the signal itself, because it does not change. If they assumed it did, every GPS calculation built on that signal would be wrong from the start. The speed of light does not depend on how fast anything else is moving. Light slows down when it passes through a material like glass or water, and that change in speed is what causes it to bend, a process called refraction. This matters because it explains why lenses work the way they do. Think about eyeglasses or a camera lens. The glass is shaped precisely so that light entering it slows down and bends at a controlled angle, which is what brings an image into focus. If the glass were shaped incorrectly or made from a material with the wrong optical properties, the light would bend the wrong amount, and the image would come out blurry. This is why prescription lenses are ground to exact curves for each person. Light travels at its fastest in a vacuum, and it slows down in materials, and that difference in speed is what makes bending and therefore focusing possible. Nothing that has mass can ever reach the speed of light. It acts as a universal speed limit, not just a description of how fast light itself happens to move. This matters because it sets a hard ceiling on how fast anything, including spacecraft, information, or particles, can ever travel. Think about the design limits engineers face when building particle accelerators. These machines can push particles extremely close to the speed of light, but never to it, and never past it, no matter how much energy is added. That limit is not a current technology gap waiting to be solved with a better machine. It is a fundamental boundary of physics. The speed of light is not just fast, it is the maximum speed anything with mass can ever approach. The speed of light directly connects mass and energy, expressed in the equation E equals mc squared. This matters because it explains why enormous amounts of energy can come from a small amount of mass, which is the basis of nuclear power and nuclear weapons. Think about a nuclear power plant. A very small amount of nuclear fuel produces an enormous amount of electricity, far more than burning the same weight of coal or gas ever could. That difference exists because the speed of light squared is an enormous multiplier connecting mass to the energy locked inside it. Even a tiny loss of mass during a nuclear reaction releases a massive amount of energy. Mass and energy are tied together by this constant, and that relationship is the reason nuclear energy produces so much more power per unit of fuel than any chemical process. A light year is a unit of distance, not a length of time, even though the word year is right there in the name. This matters because it is one of the most commonly misunderstood terms in astronomy. A light year is simply how far light travels in 1 year, moving at that fixed speed. Think about reading a news article that says a newly discovered planet is 4 light years away. That number is telling you a distance, roughly 23 trillion miles, not how long it took to find the planet or how old it is. If you mistake it for a length of time, the entire scale of the universe becomes confusing instead of clear. A light year measures how far, not how long. Because light takes time to travel, you never actually see anything exactly as it is in the present moment. You only ever see it as it was when the light left it. This matters because it applies to everything you look at, not just distant stars. Think about looking up at the night sky. The light from the sun you see left the sun about 8 minutes ago, and the light from more distant stars can be years, or even centuries old by the time it reaches your eyes. A star could theoretically no longer exist, and you would still see it shining, because its old light is still arriving. Everything you see through light is a small delay behind the present, whether that delay is a fraction of a second or thousands of years. GPS satellites have to correct for timing effects tied to the speed of light and to relativity, or the location data they send back would drift and become inaccurate. This is the important part because this single correction is what keeps every phone and car navigation system pointing to the right spot on a map. Satellites orbit at high altitude and high speed, both of which affect how their onboard clocks run compared to clocks on the ground. Engineers built these corrections directly into the GPS system from the start. Think about driving using a navigation app. If those relativistic timing corrections were removed, position errors would build up by several miles within a single day, making the system essentially useless for real navigation. The speed of light is not just a background fact for physicists. It is a working part of a system you rely on every time you check directions. Traveling faster than light would break the order of cause and effect, which is why physics treats faster than light travel as forbidden rather than simply difficult to achieve. This matters because it is not a limitation of current engineering. It is a structural rule of how the universe works. Think about 2 events happening in sequence, one causing the other. If something could outrun light, different observers could see the effect happening before its cause, which breaks the basic logic that causes come before their effects. That is not just strange, it is inconsistent with how information and events are allowed to relate to each other. This is why faster-than-light travel is not treated as a distant engineering goal. It conflicts with the basic structure of cause and effect itself. Let me show you exactly how this works using something you have probably used this week, your phone's GPS while driving. Each satellite overhead sends a time-stamped signal down to your phone, and that signal takes a measurable amount of time to arrive, because light is not instantaneous. Your phone then calculates its distance from each satellite by timing exactly how long that signal took to arrive and multiplying by the fixed speed of light, 299,792,458 meters per second. At the same time, the satellite's onboard clock is running at a very slightly different rate than clocks on the ground, because of its altitude and its speed, so the system has to apply a relativistic correction to keep the timing accurate. If any one of these pieces were missing, if the speed were treated as variable, or the relativistic correction were skipped, your position on the map would drift further off with every passing minute. 4 separate pieces, the fixed speed, the timing calculation, the relativistic correction, and the universal speed limit that makes the whole system predictable, all work together in that one moment your phone shows a blue dot on a map. Here's what people most often get wrong. The first mistake is confusing the speed of light with the speed of electricity moving through a wire. It is easy to confuse because both feel instant in everyday use. The fix is knowing that electrical signals in copper wire travel meaningfully slower than light does in a vacuum, which is part of why fiber optic cables, which use light itself, can move data faster than traditional copper wiring over long distances. The second mistake is treating a light year as a measurement of time instead of distance. It is easy to confuse because the word year is built right into the term. The fix is remembering that a light year always describes how far light travels in a year, never how long something took. The third mistake is assuming the speed of light might as well be infinite for everyday purposes, since delays are usually too small to notice. The fix is pointing to something concrete, like the visible lag on a satellite phone call or an overseas video call, as proof that the delay is real and measurable, not zero. The fourth mistake is believing the speed of light changes depending on how fast you or the light source are moving. It is easy to assume this because it matches how speed works with cars or thrown objects. The fix is remembering that light's speed stays fixed for every observer no matter their own motion, which is one of the strangest and most reliable facts in physics. This understanding matters in specific, practical situations. If you are choosing between satellite internet and fiber internet for a remote property, satellite service has a built-in delay caused purely by the distance the signal has to travel to and from orbit. And no equipment upgrade removes that delay, while fiber does not carry that same penalty. If you watch a live news segment being reported from overseas, understanding the fixed speed of light explains the short delay between the question and the answer, so you stop assuming it is a technical glitch on the broadcast. If you use a laser measuring tool on a job site, knowing it depends on the fixed speed of light explains why it stays accurate over long distances without needing constant recalibration. If you read about a newly observed star or galaxy, understanding that its light may have left it thousands or millions of years ago prevents you from assuming the object looks the way it does right now. If you ever compare internet plans that advertise unlimited speed or near-instant response times for services hosted on the other side of the world, you now know there is a physical floor on that response time that no marketing claim can remove. You can now explain why any long-distance signal, whether it is a video call, a satellite broadcast, or a GPS fix, has a delay built into it that no technology can fully remove. You can correctly identify a light year as a distance every time you encounter the term, instead of mistaking it for a length of time. You can recognize why nothing, no spacecraft, no signal, no particle, can ever travel faster than light without breaking the basic order of cause and effect. You can look at a satellite dish, a fiber connection, or a night sky full of stars and understand exactly what is happening behind each one. This is the explanation you should have gotten the first time you learned about this. Clear, complete, and finally making sense.